we're going to learn how to use exponential and logarithmic equations to solve real-world problems. And we're going to start by using exponential equations to look at money issues. So, when you put money into a bank, it's called compounded interest because some number of times a year set by the bank, your interest will start earning interest, and it gives you more money quicker. So the formula for this is given here, where A is the ending amount, P is what we call the principal, which means the beginning amount, R is the interest rate, always translated to decimal instead of percentage form, T is the number of years, and N is the number of compoundings per year. So let's look at an actual example. Suppose I put $10,000 into a savings account that earns 5.4% compounded quarterly. Okay, I want to know two things about this. I want to know how much I'll have after 7 years, and I want to know how long it will take to triple my money. We call that the tripling time. So first we're going to start by just plugging in the generic things about the problem. We know the principal is $10,000. We know the interest rate is 0.054 and that the number of compoundings a year is 4. So this is our formula for the problem. Now the first question says, how much will I have after 7 years? So we're going to plug in 7 for t and compute what we have. Now, this is the answer, but it doesn't look very good. So this is where we pull out our handy calculator. Don't forget that this problem needs the dollar sign in front of it because I'm actually computing an amount of money. And your calculator will tell you that this turns into $14,556.77. Now, for the second question, the tripling time, we want to know how long it takes my money to triple, meaning how long is it going to take until I have $30,000? So this question is harder to answer because I'm not asking for an ending amount, the A, I'm asking for a time, the T. So we're going to treat this just like we learned how to solve exponential equations. First, get the exponential alone by dividing both sides by 3,000. I'm also at this point going to do a little bit of calculator work. I don't want to have to keep on writing this, so I'm going to have the calculator tell me what it actually equals. Now, to get the next step to get the time was to get rid of the exponential using a logarithm. Usually we use a logarithm that's the same base as the exponential. There's only one problem with that here. I don't want to have to take a logarithm base 1.0135. So instead, I'm going to take a natural log at both sides. And the reason that's still useful is rules of logarithms say that this 4t, instead of being written there, can be written here. And then all I have to do to solve this is divide out by the pieces that t is multiplied by. Okay, so then I pull out a handy calculator again, and it tells me that this is 20.48. And again, it's a word problem, so don't forget the units. The units on t were years. Okay, all right, now, there's another formula for compounded interest, and it's the continuously compounded interest. A equals P e to the RT, where A, P, R, and T have the same meaning as over here. Okay. What this is a theoretical thought experiment of what if we compound more and more often a year, is there going to be a limit to how much money I can get? And the answer is yes, this is that limit. Okay. Now, no bank in the world is going to give you continuously compounded interest. They just aren't going to do it. The reason we use this formula, though, is because it is so much easier to use than this one. So when we're doing calculations that don't have to be exact, or we're just approximating, we like to use this formula because it's so much easier to use. So let me give you an example. Okay. In 1626, a Dutchman by the name of Peter Minuet came to Manhattan Island and purchased the right to use Manhattan Island from the Native Americans that were living there for $24 worth of beads. Now, when I was first told this story, they were using it as an example of how poorly we had treated the people of that time because, oh my goodness, we bought Manhattan for $24. Clearly it's worth more than that. Now, I'm not saying that that's not true, but we actually need to be careful because that was $24 in 1626. And there's a thing about money. Money back then was worth a whole lot more than money now due to something called inflation. So if we take a fairly standard average rate of inflation of 6% a year, how much would that $24 from 1626 be worth in 2016? And that's a totally different question. So first we need to know how much time has passed. So I'm going to take 2016 minus 1626, and that gives me 390 years have passed since Manhattan Island was purchased. Then I'm going to plug it in to the formula. So the amount that $24 turned into is 24 times e to the 0.06 times 390. All right, so this is going to be in dollars again, and this is where things get interesting. All right, hundreds, thousands, millions, 348 billion, 900 million, $922,914.58. Now that still may not be the actual value of Manhattan Island today, but it is a whole lot closer than what we originally think when we say $24. So you need to be very careful when you're doing money problems that you're not thinking of things when they were worth a different amount.